we are going to take transpose of matrix, and it's a very simple operations to understand. In case of a matrix transpose operation, we have already seen some of the operations in last lecture, wherein in the last orthogonal matrix we have seen that the transpose of a matrix is been applied. Okay, so we'll see first of all by using some simple example how the matrix transpose is defined. Right. So some students might be already known to this concept, that is transpose of a matrix, but some students may not be like heard about transpose of a matrix, or they might have heard but they don't remember it clearly. So that's why we'll revise it by using a simple example, and then we will see how transpose of a matrix is calculated by using Python. Okay. So what I'll do is I'll consider one matrix of order 3 by 3. Okay. And then we'll convert it into, and we'll take a transpose of that matrix, right? So I have taken here matrix A with 3 rows and 3 columns. So I'll take this numbers as the row number, so that when you transpose it, you will understand that how the transpose is going. Okay. So you can observe here, there are 3 rows and 3 columns I have taken. I'll mark here by using the row number, that is R0, then R1 and R2. Similarly, I'll mark here the column numbers, that is column 0, column 1 and column 2. Okay. So in this case, what we are going to do is we are going to convert this rows into the column. That is called the transpose operation. Okay, sorry, I forgot to share the second screen. Wait for a few minutes. I'll share the second screen. Right. So what we have created here, we have created a matrix of order 3 by 3, right? And you can see here, we have created a matrix, row 3, that is 3 number of rows, 1, 2, and 3. I given here the name to these rows, that is row number 0, row number 1, and row number 5 is the row index. Similarly, the column index has been used to name the columns, column 0, column 1, and column 2. So transpose of a matrix is nothing but, many students have written in the chat window that it is a conversion of rows into the column. Okay. What we have to do in the matrix inversion, when you invert the matrix or take a transpose of a matrix, the matrix transpose is the rows of a matrix are converted to the column, right? And the transpose of a matrix is used in many applications, as we have seen in the last example, in the last lecture, that is to find out whether the matrix is orthogonal or not. Okay, if A into A transpose is equals to an identity matrix, then matrix is an orthogonal. Okay, and for getting to know that whether the matrix is orthogonal or not, we have to take the multiplication of a matrix with its transpose, and in that case, we have to find out the transpose of a matrix. Okay, and hence we will apply the transpose on matrix A. Transpose can be denoted in multiple ways. That is, say, one of the ways to denote matrix transpose is using this apostrophe. Okay. The second one is you can represent matrix transpose by using this T. Okay. Sometimes a capital T is used, or sometimes we use like a small t. Okay. So there are different notations followed, different books. Okay, so this is on superscript. Okay, A apostrophe, that is A dash, is called as A transpose, or A superscript small t or capital T is also used to represent transpose of a matrix. Okay. So by definition, what we have said is transpose of a matrix is nothing but the conversion of row into the column. Okay. So if you assume matrix A, then transpose of a matrix A will be, okay. So see, this first row is now been converted into the column. Okay. So first column it will be C, right? Similarly, second row is converted as a second column. So this will be my second column, and this third row becomes the third column. Now you can see here what has happened. The row 0 has been converted into the column 1. Row 0 is converted into the column 0. Row 1 is converted to column 1, and row 2 is converted into the column 2. And this new matrix, we call it as a transpose of matrix, right? So this is how you calculate transpose of a matrix. I hope it is clear to you all that what is a transpose of a matrix and how a matrix transpose is calculated, right? So in case of a Python, you don't have to do these operations explicitly. Python have an inbuilt function available under NumPy library. We will use that function directly. We'll apply it to a matrix for which we have to calculate a transpose, right? We'll see this example on Python collaboratory, right? So this is an example. We have taken here a matrix of order 3 rows and 2 columns, right? So I have displayed the matrix A. I'll write here and print what we are displaying. We are first displaying matrix A, print A, then calculate the transpose. And how transpose is calculated? By using dot T. This is a very, very simple operation to remember. Okay. So I have assigned capital C is equals to A dot T. This A dot T operation, what it will do? It will calculate the transpose of matrix A, and it is stored in the C. So what is C here? C is a transpose of A, and I'll print here, print what we are displaying. We are displaying transpose of A, right? So we are displaying a transpose of A, and we'll see according to the definition what we expect here. If A, I'll again display the shape of this matrix, and I'll write here print A dot shape. Okay. Also print here so that we want to know that when we convert the number of rows into the number of columns, then the shape of a matrix will also get changed. Okay? So that is also we want to note down. And similarly, because here it is not a square matrix. If you observe here, it is not a square matrix. That is, the number of columns are not equal to the number of rows. Right? Here we have a rectangular matrix where number of rows are 3 and the number of columns are 2. Okay? So hence, when we convert the matrix and we'll have a transpose of a matrix, so this, observe here, row 0 becomes my column 0, row 1 becomes my column 1, and row 3 becomes my column 3. So original matrix is having a shape of 3 rows and 2 columns. However, when we take a transpose of such a matrix, it will convert number of rows into the number of columns, and hence number of columns becomes number of rows. So original matrix of size 3 rows, 2 columns. Then after taking a transpose, we have a dimension of 2 rows and 3 columns. That will see how it is. And hence, I am going to print here the size of this matrix. Okay, size of, I can say, transpose. Okay. After taking a transpose, we have stored it in this. So I'll execute this. And you can observe here. First, we are displaying the size of matrix A, which will return 3, 2. Right? So we can say size of A, 3, 2. Then we have a matrix A, 0, row 1, and row 2. Then after taking this, we have a transpose of a matrix. So what's happened here? See, this 1, 2, 3 is being converted into the column. Okay. So this 1, 2 is it goes into the column. 3, 4 it goes into the column. 5, 6 it goes into the column. And hence the size of a transpose matrix is 2 rows and 3 columns. Right? I hope it is clear to you. Again, this second example that how transpose of a matrix is actually calculated and how the shape or the size of a matrix get changed, or the transpose of a matrix will have a reverse size, that is number of rows is being converted to the number of columns, right? So I hope there should not be any question because it's very clear to understand what the transpose matrix is, and then we're going to start with next operation. Okay. So next operation is inverse of a matrix. Okay. So what is the inverse of a matrix? Many of you might have used matrix inverse or calculated the matrix inverse. How we define matrix inverse? Okay. If students have given an answer, transpose A inverse is equals to, okay, 1 divided by determinant of A into adjoint of A, right? Okay, very good. Adjoint of a matrix divided by determinant of A. So I'm going to tell you some of the important properties of a matrix. Like someone has asked me a question, I haven't answered it right now because I know that somewhere we are going to discuss it in the next topic. So I didn't consider it, but I will consider. Um, Shreyasi, okay, Shreyasi asked that why inverse function is used in orthogonal matrix. Okay, so what has happened in the orthogonal is we try to find or try to define an orthogonal of a matrix in a two-way. Okay, number one is by using transpose of a matrix, and second one is by using inverse of a matrix. Okay. However, in the last example, we might not have applied it. We only applied the transpose of a matrix, but both of them have worked equally. Okay. And that we will see through an example. I'll demonstrate with you. You can observe. The first property is for the inverse of a matrix. It says that if we take a matrix inverse, then a matrix A into, if you take A inverse, right? Then it will return you identity matrix. Okay, so you can see here that how the operation is performed. Okay, and the second property is it is for right here for orthogonal matrix. We we have the operation that is matrix A. So you can observe here the matrix A multiplied by 8. Okay. So what this actually mean is both the operations are having the same meaning. For orthogonal matrix, okay, wait. Okay. I just read about the chart window. Okay, just wait for 1 minute. Now it is visible. Okay, now see, right. So see here, first property I told you, that is about the inverse of a matrix. When inverse of a matrix is represented by A superscript -1. Okay, that is called as an inverse of a matrix. Okay, so in this property, the first property, what it says that the matrix multiplied by its inverse always give you identity matrix. Okay, so this is the first rule about the inverse of a matrix. And this rule actually we applied in the last example. But what we did is, for specifically for orthogonal matrix, we performed an operation that is A multiplied by A transpose, which actually return you the matrix identity. Okay. So if you remember from the last lecture, when you performed A multiplied by A transpose, it returned you an identity matrix. Okay. So what actually this operation means? It means that for orthogonal matrix, the A transpose, okay, and A inverse are equal, right? That means if you take A transpose, then it is equals to an A inverse. This is what an orthogonal matrix is exactly defined in the second, what I can say, definition. So that's why we try to use an A transpose, right? So this is what we tried in the last example. Okay. Now listen here, what we are defining A inverse. A inverse can be represented as this A superscript -1, and in case of a Python, we will have an inverse function. So what I am trying to tell you here, Shreyasi, you asked that in last example, we applied A multiplied by A transpose and we found that it is equals to I, that is an identity matrix. What does it mean here? That is A is the same matrix in equation number 1, or say property 1 and 2. Second one is A is multiplied by A inverse in the first property, whereas in the second equation, second property, we multiplied A with the A transpose. If both of these are returning I, then in that case, for matrix A, we have A inverse is nothing but A transpose. Okay, and hence, if this property has been satisfied by a matrix, then that matrix is called as an orthogonal matrix. Okay, and hence, in case of orthogonal matrix, we try to calculate, or we try to find out the inverse as well, and we try to define it by using the inverse also. So now we will go and we'll see the example. Inverse of a matrix can be calculated in 2-3 ways. There are 2 to 3 ways to find out the inverse of a matrix. Okay. Number one is you told it by definition, that is 1 divided by determinant of A multiplied by adjacency matrix of A. This is one of the definition. Second one is by using this first property number 1. What you will do is you will try to convert this A inverse has not been defined only. Okay, you will try to convert this identity matrix, this A inverse, into the identity matrix, and you will have here the matrix A inverse, that is called as a row and column operation. Okay, so there are 2-3 ways to convert it. However, in this particular class, we are going to learn linear algebra using Python. So in case of a Python, actually it is this linear algebra we are going to apply on a machine learning, and specifically when you study deep learning concepts where the matrix size is of thousands of elements. Okay, or I can say that there are, like, say, more than hundreds of rows and hundreds of columns present in a matrix, which represent actually the pixels of an images, right? So in that case, to apply this particular definition and to calculate a matrix inverse manually, it's next to impossible. Okay, to take those large values and to apply this inverse operations or transpose operations, right? So in that case, what you will use is always you will be going to use inverse function from the Python NumPy library, right? So we'll go and see how easily or how easy it is to find out the inverse of a matrix and by using a Python, right? So I'll share this screen. So you can see inverse. So what we have done is we have first imported array function, and then specifically from a linear algebra library, I imported INV function. So what is now clear to you all, INV is a function to calculate an inverse of a matrix. Okay. So first, by using function array, we have defined a 2 by 2 array, 2 rows and 2 columns with elements 1, 2, 3, 4. Then I have displayed matrix A. So I'll write here print. Can you tell me what you will get in a inverse? A matrix of same size. Huh? So after taking an inverse of a matrix, print here, calculate the matrix inverse, and I'll store it into a B. Okay, here matrix B is equals to what? INV inverse of matrix A. So I'll print here, that is inverse of A. And we'll execute this. So you will have first this operation you will see after this later. So we will see here the matrix A is displayed, row 1, row 2, and the inverse of a matrix A is calculated, and here we have an inverse of a matrix. Okay, those who wanted to like verify whether the Python is doing correctly or not, they can calculate the inverse of a matrix by using the manual method, and they can try this. But I know that Python is doing good, and they are like calculating the inverse correctly. Okay, so only if you wanted to do good. So according to the first property, as we have seen, we are going to verify the first property, right? So what is your first property? So this is my first property, and we'll go and verify this property. Right here, INV is inverse of A. So A multiplied inverse of A, what you will get? Identity. And I'll try to verify this property. So what is A? A is my original matrix. Okay. And what is B? B is a inverse of it. You can see here I have highlighted. So A is my original matrix and B is an inverse of a matrix A. Right? So I have calculated the inverse of a matrix, and then what I'll do is I'll do a dot product, that is I'll multiply matrix A with matrix B, and I'll try to find out whether I'll get an identity matrix or not. Okay, so this is actually what we have is it is near to 0, right? So what I can do here, I can convert it to an integer. Okay, so what I did here, just listen. Hello. So actually, we have taken an inverse of a matrix A, and then what we did is we multiplied A with A inverse, and then what we have done is we have converted it into an integer. Actually, it was a float, so it was saying 1.0000 something like up to 10 16 decimal places. Okay, and when actually when you do it by using pen and paper, we always are happy to write it up to a 1 or 2 decimal places. Okay, and hence when we have it like to be converted, then it will consider it like this. And actually, what here we are expecting 1, but due to as a type an integer, it has considered even a 0.5 for the lower, what you can say, lower decimal place. Okay, and hence the 0 is then printed. But when you go and calculate it manually, you will find it that here it will be the 1. Okay. So we will go and we'll find out the next operation, and that is called the trace of a matrix. Okay. So trace is again an important property of a matrix, where we are calculating the trace as sum of diagonal elements. Okay. So you can write down the definition of a trace of a matrix, and we will use trace of a matrix in many applications. There are many applications of a trace of a matrix, and trace of a matrix is defined as sum of diagonal elements. So for example, let's say if A is a matrix here, so what will be the trace of a matrix for A? By definition of a trace, what is a trace? We have defined trace as sum of diagonal elements. So when I say diagonal element, it's always a main diagonal. Okay, main diagonal, that is from top left corner to the bottom right corner. Okay, so that is 1 and 4. These are the elements of main diagonal, and you take the sum of this main diagonal elements, that is 1 plus 4 equals to 5. This is the trace of a matrix. So we'll see an example of a trace of a matrix. Say this is a matrix defined. So which are the diagonal elements of this matrix A, and what will be the trace of this matrix? For this matrix, which are the main diagonal element and what is the trace of a matrix? Yes, okay, right. So many of you have given a correct answer. So main diagonal element is 1, 5 and 9. These are the elements of main diagonal. And if you take a sum of these elements, that is 1 plus 5 plus 9. Okay, that is equals to 15. And that is nothing but the trace of a matrix. Okay. So properties of a trace of a matrix is being used for many applications, like in case of eigenvalue, for transpose, and many different things. Okay. So depending upon the value of a trace of a matrix, we can have many different conclusions about the eigenvalues, eigenvectors of the matrix, number of eigenvalues, whether the eigenvalues are imaginary or whether the eigenvalues are zero or non-zero eigenvalues. That these properties are associated with the trace of a matrix. Okay, and hence trace of a matrix is very important to know and to calculate. So for a trace of a matrix in Python, we have a function called as a trace, which is available under the library NumPy itself. Okay, and we apply this function trace to array A and calculate the trace of a matrix. So trace of a matrix is a scalar quantity; it's a single value. Right? So B here will not be an array, however, B will be a simple scalar value, which is nothing but sum of diagonal elements. We'll execute this, or we will write here what we are displaying in the output. So we are first displaying matrix A, and after that we are displaying print trace of a matrix. Okay. You can have here in the output, that is matrix A displayed, and as many of you have given a correct answer, trace of a matrix A is 15. I hope it is clear to you all the three operations. That is, number one, we have seen inverse of a matrix, determinant. Then we'll be going to see determinant of a matrix. Okay? So, determinant of a matrix. Can anyone tell me what a determinant of a matrix is? Then we'll see the matrix determinant. How we'll calculate the matrix determinant in Python. In case of this Inverse of a matrix. We have defined inverse of a matrix is equals to 1 divided by determinant of A multiplied by adjoint of A. Okay. So there we have actually calculated first of all the matrix determinant. Okay. I don't know the name of the student. I told you to do, when you log into the WebEx session, you should have your name defined properly. Okay, there is an option to define your name in case of a participant list. Okay, you check participant list, check your name there, and by clicking on your name, you can print it. Otherwise, these random names, we don't know that who is the student giving an answer, or who is the student attending a session. So he has defined that inverse, that is determinant of A is nothing but magnitude of A. That is even a very good and correct answer. Many students, like many people find it difficult to understand, but yes, it is determinant of A is called as a magnitude of A, and this is again a scalar quantity like a trace of a matrix. Okay, so like in case of a transpose of a matrix, we got in return and another matrix. Okay, in case of a inverse of a matrix, again we have a different matrix of a same sign after taking inverse. But when we calculated trace of a matrix, we got a scalar quantity, a scalar value. How similarly in determinant of a matrix, we will get a scalar value, a single value, which tells about the magnitude of a matrix. Okay. So it's very good that many students knows about this basic concept related to the linear algebra, and it is very easy for me to define this in terms of a Python. Okay. So determinant of a matrix calculated in Python by using function det. Okay. And this det function, determinant function, is available under library called linear algebra. So we imported our regular function, that is array, define an array of some size, specified size, and then we have imported from linear algebra a function called determinant. So here first we have defined an array of size 3 by 3. We have displayed an array here. First, say matrix A. Then we have calculated determinant of A and we have stored it into a new variable called B. Okay. So how I have written here? A is equals to det determinant applied to A. Actually, you all have to note down certain nomenclatures here. That is how functions are applied. Right? So trace, we have supplied this A. For dot product, actually we supplied B, and before it is multiplied with A. Okay. Similarly, in inverse is a function, so we have given an input that is a matrix A. So if you remember this nomenclature, then it will be very easy for you. If you know the function name, you can apply it without knowing the syntax. Okay. So that means what I mean to say here, when I say it is a function, that means this will have an opening closing round bracket, and we must know a variable on which we need to apply this. Okay. So I need to apply this function determinant on matrix A. So that will be my input. Right? Because sometimes we may end up in writing a wrong syntax or calling a function with some error. Okay. So we should not call a dot determinant or something like that. Okay. So determinant is a function which will be called by giving an input as a matrix for which we have to calculate a determinant. Okay. Similarly, the inverse will work, INV inverse in bracket, a matrix as input for which we have to calculate an inverse of it. And same is the case of a transpose. Okay. So that means these all are the functions which will take a single parameter, and that parameter is nothing but a matrix for which we have to calculate a respective operation, or for which we have to perform a respective operation. So this syntax you have to note down, and so that once you know the syntax, by just understanding that what is the function name, you can apply this properly to a given matrix. So I'll display here. So you can print, that is determinant of A. We have this matrix A here with values 1, 2, 3, 4, 9, and determinant of A is equals to. Here determinant of A is 0.00. There is a second property according to the definition of an inverse, that is, if we say the inverse of a matrix is equals to defined as, that is, 1 upon determinant of A multiplied by adjoint of a matrix. Okay? So I'll repeat the definition. If you define a matrix, inverse is equals to 1 divided by determinant of A multiplied by adjoint of A. Okay? If you use this definition, then according to this definition, if A inverse we have to calculate, then we need to ensure that determinant of A should not be equal to 0. If for any matrix determinant of A is equal to 0, then in that case the A inverse will not exist, because 1 upon determinant of A, that means 1 upon 0 will be an infinite term. Okay? 1 upon 0 will return you an infinite. And hence, in that case, the matrix determinant is not, matrix inverse is not calculated. And here, sometimes you will require this determinant of A to be calculated separately. Because if you directly go and calculate inverse of A and it will return you, it will throw some error, and then you don't understand that what has gone wrong and why the error has been occurred. So in that case, what you can do is always, whenever you require to find out the inverse of a matrix, calculate the determinant of a matrix, right? So in case of a determinant of matrix, if you are getting 0, then it is very clear that the matrix A don't have an inverse, right? So this is an important property which can be verified by using a determinant. So we can change some elements and try to see that whether the matrix A can be changed, right? So we have some different values. So we change this matrix A. So now here we got a determinant that is minus 77. So you can see here, as I told you in the previous example, that it's by default calculating a float value with up to like 15 decimal places, right? And if you want to convert it into an integer, you will use this function as dot integer. That is a variable which you want to convert into integer, and then you need to type as dot integer. So that you can use it. So determinant here it is minus 77, which is not equal to 0, and hence you can say that now matrix A have a inverse. So you can calculate the inverse of this matrix, right? So I hope it is clear that what is a determinant of A, and then we will see what is the rank of a matrix. This is again a very, very important topic which comes under the linear algebra, that is to find out the rank of a matrix. Okay? So how we define the rank of a matrix? It's very simple, as like in transpose of a matrix. Rank of a matrix is nothing but actually the total number of non-linear, or in a very, very simple language, if I want to define a rank of a matrix, it is nothing but the total number of non-zero rows. Okay? Total number of non-zero rows, or the total number of, or the maximum number of non-zero columns. So if we calculate the total number of non-zero rows or the total number of non-zero columns, so if they are different, that is number of rows are different or number of columns are different, then in that case, the minimum we have to take. Okay? In that case, we take the minimum value, whichever is minimum, right? So if we have the number of columns less than the number of rows, then we will take the number of columns parameter. Or if we have the number of rows less than the number of columns, or we can say non-zero, number of rows are less than the non-zero number of columns, then that value will be your rank of a matrix. Okay. So for now, just remember a single line that rank of a matrix is nothing but total number of independent or total number of non-linear or total number of non-zero rows. Okay. And we'll see one example on this, and we'll try to understand more about the rank of a matrix, how it's calculated. As I said, rank is the total number of, that means it is going to give you the count, which is how many number of rows which are non-zero. And hence the rank of a matrix will be a scalar value. And to find out the rank of a matrix, we will have here a function called as a matrix underscore rank. Okay. So to calculate the rank of a matrix, function name is matrix underscore rank, which is available under linear algebra library. Okay. So I have actually defined here an array of 1D, a vector. A vector can also have a rank, because we are actually calculating independent rows. So instead of taking a vector, I will take here a matrix for your understanding. So this is row 1, comma, row 2 will be and row 3 is say so now this is a matrix say M, print M, then I'll calculate me say rank and unit by R, so rank of M. Okay. So I'll apply the function matrix underscore rank to M, and then I'll print the rank of M. Okay. So now we'll see here, we have defined a matrix M with 3 rows, row number 1, value 1 to 3, row number 2 with value 2, 1, 2, and row number 3 with values 0, 0, 0. So now matrix M is of order 3 rows and 3 columns. I displayed here, that is, say print matrix M, and then I print here rank of matrix M. Okay. I will execute this and we'll see this. Now, by definition, as I told you, the definition of a rank matrix is nothing but total number of non-zero rows or total number of non-zero columns. And amongst them, we have to take the minimum, whichever is minimum, right? So, by this definition, would you like to try and tell me the answer of this? What will be the rank of this matrix A, matrix M? Okay, write it in the comment section. Okay, very good. Many students have given a very correct answer, that is 2. But few students, 3 students have given answer is 1. I don't know. I wonder that how they calculated rank of matrix 1 is. So now listen here. If you observe, the first row is having elements 1, 2, 3. Okay. When I say a non-zero number, non-zero row, non-zero means all element must be non-zero. Okay? Or we can define it as the row. See this last row and observe the elements in the last row. The last row contains elements 0, 0, 0, and such a row we call it as a zero row. That means there is no element, all elements are 0. So this row we will not call it as a non-zero row. Okay, this is a 0 row. It is not a non-zero. So first row is my non-zero row. Second row is also my non-zero. Okay. So we have two rows which are non-zero, and hence we can define it that the matrix inverse is equal to 2. Okay, and now we will calculate it by using this Python. I can see. All right. Okay. So now you can see here, we got one error, and this is very important. Just observe here what the error is saying. See here, what is your matrix is 1, 2, 3, and it is 2, 1, 2, and it is 0, 0, 0, right? So now just observe here, I'm telling you a very important concept related to the rank of a matrix. Actually, when we define a rank of a matrix, we have just said about that rank of a matrix is nothing but total number of non-zero rows or non-zero columns. But as far as mathematical operations are considered, rank of a matrix is calculating actually the total number of non-linear rows or total number of non-linear columns. And those non-linear rows and non-linear columns are calculated by applying a function called row and column operations. That means, is there any way so that I can convert a particular row or a particular column into completely zero? Can I perform any operations? Right? Okay. So say for example, if I apply an operation here, that is column 1 plus column 2. Or if I apply an operation that is column 1 minus column 2. Okay. If you apply an operation column 1 minus column 2, then in that case, what will happen? It will convert it into 1 minus 1. This column will be a 1 minus 1. Similarly, this operation can be applied to this column. And in this way, what we can do is we can convert one more row or one and more than one column into a zero column. Okay. So when you apply like this, it will get converted into the row and the column with zero operations. And here's what it is saying that you can observe here. I calculated the rank of a matrix is equals to, the function is what? Matrix underscore rank applied on M. Okay. So we will see first of all, consider one example. Okay. Now consider this matrix A. So see here, right? I'm telling you one concept related to the rank of a matrix. So by simple definition, we have just said that it is total number of non-zero rows or total number of non-zero columns. Okay. Now we can see here according to this. So by observing this, can anyone tell me what is the rank of this matrix A? Okay. So now I understood, as I told you a definition. It is very clear according to a definition. Now just listen here. According to a definition, your answer is very correct. That is, total number of non-zero rows is nothing but the rank of a matrix. But we have a definition which says that non-zero, I mean to say that non-zero means they should not be linearly dependent. Okay. That means if I apply some operation on this row or this row, can I convert it into a zero row? I can easily convert. Okay. Say for example, number one operation I can do by using row 1, that is, say R1, row 1 is equals to, what I say, row 1 minus row 0 multiplied by 2. Okay. And second operation that I can do is row 2 is equals to row 2 minus row 0 multiplied by 3. So you apply these operations and you tell me what will happen. What will be the new matrix? So after applying this operation, what will happen is I have applied these operations on these two rows. Okay. So applied these two operations. First operation I applied on row number 1 and second operation I applied on row number 2. So when I consider this operation, what will happen is row 1 will be converted into 0 and row 2 will be again 0. Now is there any chance and I can convert it again into, I can convert the row, this row into a 0 row? No, there is a no chance. Now very clearly only one row is remaining which is a non-zero. Okay, there is only one row which is a non-zero. Even if you apply a column operation, say for example, but try to perform this operation, like number 1 is column 1 C1 is equals to C1 C1 minus C0. Okay, and if I perform second operation, that is C2 column number 2 is equals to C2 minus C0. I can perform this operation. Okay, if I try to perform this operation and calculate this, we will have a matrix A. After performing this operation, what I will have here, this column is converted to 0 and this column is converted to 0. Okay, but still I can highlight over here, you can check this row 0. Is it a non-zero row? Whether all elements are 0? No, it's a non-zero row. It is not a 0 row. Similarly, this column. Okay. So we cannot say this row 0 is a 0 row, or we cannot say this column 0 is a 0 column. Okay, because there is still one element remaining which is a non-zero, and hence it has been made this row 0 as a non-zero row and this column 0 as a non-zero column. So now we have total number of non-zero rows equals to 1 and total number of non-zero columns equals to 1. And hence for this particular matrix A, the rank is 1. Okay. So rank of this matrix will be 1. And this is what I wanted to tell you. So whenever you will see an example, then just by observing an example and calculating the non-zero number of rows or the columns, you cannot directly tell that this is the rank of the matrix. Somehow you will have to go further and do some mathematical calculations and try to understand whether there is any row or column which I can make a 0 or which I can convert it into 0. Okay? And if you can do so, then the rank of a matrix will get changed. So this you have to do when you manually calculate the rank of matrix. Okay, I'll repeat it. These things you have to do when you manually calculate the matrix. But in case of a Python, when you apply this matrix rank function, it will calculate implicitly for you and it will simply tell you a scalar value about the rank. Okay. There is a question from Harsh Sahu. You are correct that according to a definition, it is maximum minimum number, a maximum number of non-zero rows or the non-zero columns. But you will have to check it whether the rows are dependent on each other. See, row 1 is dependent on row 0 because it is a multiple of row 0. And this is what a mathematical definition says. Okay. And yes, according to the first definition I told you, the very first definition I told you, that is number of independent rows or number of independent columns. But in a simpler way, you can define it as a count of total number of non-zero rows, because in case of a total number of non-zero rows, we are calculating non-zero rows after applying this function, whether they are independent or not. Okay. So you will have to remember this. From next time onwards, you will have to remember this, that the total number of non-zero rows are applied only when the rows are independent. Like here. Here you can calculate the total number of non-zero rows because all rows are independent. They are not dependent. They are not multiple of each other. Okay. And hence you can go ahead and apply this definition to this. Okay. I'll go to our previous example and we'll see. So don't worry about we're not going to manually calculate the rank of a matrix. I'm going to use this function. Okay. So you will always get a correct answer, but only to cross verify it, you must know some properties of a rank of a matrix. Okay, or you must know that how it is being calculated, so that sometimes by chance, if it happens that you end up with some error, then you must know that the logic behind it, that what is happening. Okay, and so that you must always know all the properties of all these operations, how it is being performed, how it is being calculated. Actually, whatever operations we have seen till now on matrix, on vectors, on arrays, okay, on all these things. Actually, Python does all these things. Okay, you don't have to explicitly code and to write a function for this. But what is very very important is, important thing is that you must understand that what is an operation we are applying and what we expect in the output, right? As a programmer, you must know, or you must be able to be in the position to decide that the output we are getting is a correct or not. Because always sometimes happens that it is not a syntactical error, it is a logical error, and you always get an output, but output is incorrect. And why the output is incorrect, you must be able to figure it out, right? And to figure it out, you must know that what is the rank of a matrix and what we are expecting to calculate in the rank of a matrix. Okay? If you get another matrix in the rank of matrix, that means something is wrong. In case of a rank of matrix, if the order is 3 by 3 and if you are getting a rank of matrix 4, this is obviously wrong because the number of rows and columns itself is not greater than 3. Okay? So such things, such basic properties, if you know this, then you can figure it out what is went wrong in your code. Okay, what is went wrong in the output. And for this only, we are trying to understand the properties of each function and how the function is actually work, and then we apply directly built-in functions available in the cloud. So we have displayed here the matrix A first with values row 1, row 2, and row 3. And as I try to convince you that you will have to again go and cross-check it whether by applying some row or column transformation are we able to convert any number of rows or columns into the 0 row or a 0 column. Okay? If this is the case, then the rank of a matrix may not be equal to what we are going to see right now as in total number of non-zero rows or the columns. Okay? So here you will have here what I did here now. I executed this. Okay. So the rank of a matrix is 2. Now I'll take one example from our previous example. That is, we have a value that is 1, 1, 1. First row, this is second row, and this is third. And then we'll calculate here rank of matrix. So in this case, row 1 was the example which we have seen in the Excel, that is the row 1 with all element 1, row 2 all element 2, and row 3 with all element 3. So display the matrix 1, and you can see here it has correctly calculated the rank of the matrix, that is 1, by performing row and column transformation. So Mayuri Shivarkar is asking, not understood. So what exactly, if you tell me the line number which you don't understood, then I can clarify it. Okay? So it's very simple that when you calculate the rank of the matrix, I'll take one more example. You see here, that is, say, this is a matrix with values 1, 2, 3, and another matrix with values, say, 1, 2, and 3. And this is third row. So see here, okay? Tuja is asking how do you remove error? Here it was not an error of a matrix. It was an error because I didn't calculated the RM, that is the rank of matrix. I didn't apply this function and the variable was not defined. This by mistakenly this line was deleted from me, and actually I tried to print the RM and that's why the error was displayed. Okay. Then what I did is I calculated it. I placed it. Okay. If I execute it like this, okay, so it was defined earlier. I has taken this value from here. Okay, so I can remove this and I'll execute this. So actually what happened here is RM is a variable which was calculated here and it is stored in variable, okay, and hence it is taking this value. So I can say here rank, and I'll execute this function. Right, so this was an error on line number 10. What says the name rank M is not defined, and hence then what I did is I calculated here is I said rank is equals to matrix underscore rank function, and then I displayed it, and hence the error is removed. You have to read the error always read the error what it says and on which line number the error is. That is only what I did in the earlier, where nothing was wrong in the earlier code. Now I have taken another example. See here what we are doing. We are considering a matrix with row 1 as 1 to 3, row 2 as 1 to 3, and row number 3 is 0, 0, 0. So row 3 it's itself 0 from declaration itself. So you don't have to take an extra effort and try this whether it is being converted into a 0 or not. It is already a 0. But now you will see this row number 0 and row number 1 is exactly same. That means if I can do a very, very simple operation, which operation? That is R1 minus R2. Row 1 minus row 2, then one of the row will be converted into 0. Right? Any one of this row we can easily convert it to 0, and hence the total number of non-zero rows remaining will be 1. Execute this output. You can see this is a matrix. If I perform here row 2 equals to row 2 minus row 1, then this will be easily converted into 0 row. Okay? And hence I can have only one non-zero row left with rank of matrix equals to. So second very, very important property I would like to tell about a matrix and the rank of a matrix. Bansi Patel has given an answer, and even Shreyas and many students were there who said that the rank of a matrix is 0. Okay, so always remember that only null matrix. Okay, so I'll go and write over. So only 0 matrix or null matrix. So this is matrix B, and matrix B here is having all rows and all columns equals to 0. So only 0 matrix or null matrix will have rank equals to 0. Okay. So I can write here only or 0 matrix So all other matrix, which is so like say for example here matrix A is a non-zero. So matrix A here after converting here maximum number of rows or maximum number of columns are 0, but entire matrix is not 0. Okay? My entire matrix is not 0. There is still one element which is a non-zero element, and hence it is a non-zero matrix. So any non-zero matrix will have a rank minimum 1. Okay? So the non-zero matrix will have rank equal to minimum 1. Okay? Minimum, I said it is minimum. You have to note down it is minimum. it may be more than 1. Right? So there is a question from Chaitanya, what is the rank of a zero-dimensional matrix? That is a scalar value. If that scalar value is 0, then rank will be 0. If that scalar value is non-zero, then rank will be. If it is a matrix, I am telling you, if it is a matrix that it has like 1 and 2 rows, then in that case it will be 1. Okay? So like say for example, I'll go ahead and I'll tell you here an example. So you can check here. So we'll take one example here and have here matrix say M1 is equals to 1 closing square bracket was extra. Okay? So you can see it is M1 matrix M1. I have to take M1 here. So matrix M1 and see the rank is 1. Okay? If I make this element is 0, so rank of M1 and M1 is 0. So there is a one element and it is 0 itself. And hence the rank is becoming 0. Right? So I hope this is clear to you all now. And we'll see the next topic. So here there is an example which has created the rank of a matrix. Here the matrix itself was a 0 matrix. Okay, so see N0. N0 is a matrix of all elements 0. So obviously, what you will have the rank of matrix 0 and 0 is 0. So this matrix is 1, 2, 1, 2, M1. M1 is having elements 1, 2, 1, 2. So I can easily convert any row or column into a 0. And hence I'll get the rank equals to 1. This is another example wherein all elements are different and you cannot convert into any row or column into 0. And hence you can have a it says 0. So this was a 0, 0, 0 matrix and hence the rank was 0. This is 1, 2, 1, 2. I can convert any row or column into a 0 row and hence only one row or column will be left. And similarly for this, right? So I hope it is clear and now we will have two examples and then we will practice on this example. Okay, is it visible to all of you now? Question? So this is a matrix of order 4 by 4 and you have to apply the concepts and you have to calculate it. Those who are using this Python collaboratory or they have Python installed, they'll calculate the answers of 1, 2, 3, 4, 5, all these 5 questions and they'll tell me in the chat room. Okay. Okay, I hope everyone have executed this example and I got a response from many students to all the questions which we have displayed here. And now we go and see in the Python. So all students will cross verify their answer. Okay. So I'll repeat that we'll see execution of these questions on given matrix M1 and what all students will do, they'll cross check their answer because it will not be possible for every student individually to check for me. If at some point your answer is not matching to my answer, then only you can raise a question. Okay. So I will go and execute all this question on this matrix M1 and we will cross check with your answer and with my answer and if there okay, then there is no issue. If there is a difference, then we will discuss it why it has happened. Right? So see here, I have displayed a matrix. I have defined a matrix M1 as it was given in the question. I hope everybody has defined a matrix, same content, so you can cross check it whether it is correct or not. So this is a matrix with first row 2 4 1 3, second row 1 2 2 4, third row 2 5 1 3, the fourth row that is 1 to 1. Okay. So what we did is first we displayed the matrix M1 as it is. So write it M1. After that, I calculated executed question 1 to find the transpose of the matrix. So I know what is the function for a transpose of a matrix is a matrix dot. So calculated the transpose in variable TR M1 is transpose of M1, and then I displayed TR M1 that is transpose of M1. After that, next question is to find inverse of a matrix M1. So I applied the function inverse IUV on my matrix M1. I stored the result on IM1 that is inverse of M1. And then I displayed the inverse of a matrix M1 as IM1. The next question was to find determinant of a matrix M1. So I know the function is det determinant. So I define a variable dm1 that is determinant of m1 is equals to function dt applied on matrix m1. I displayed the value of determinant of a matrix m1 and I printed the value of dm. Question 4 was find trace of a matrix. So for trace of a matrix, the function is trace, and I have defined a variable tm1 for a trace of m1 which calculates the trace. So I calculated the tm1 value and I displayed it as trace of m1. After that, the last question number 5 was to find out the rank of a matrix m1. So for finding the rank of a matrix, we have function matrix underscore rank, and I stored that value into the Rm1 that is rank of m1. And similarly, I applied the function on matrix m1 and I displayed the value. Okay. So we'll go and see the output of this. So let's see this first of all. So see in the output, on the very first line, we have a matrix m1 itself. Matrix m1 is displayed as it is. Then question number 1, transpose of a matrix m1. So here we have transpose of a matrix. That is, so 1 will go to the column 1, 2, 4, 2, 4, 1, 3. Row 2 will go to the column 2, 1, 2, 3, 4. Row 3 will become column 3, 2, 5, 1, 3. And row number 4 will become column number 1, 2. So we got a correct answer. And I hope that everyone of you will get the same answer, or already have got the same answer. The next question, inverse of a matrix M1, and this is what we get as an inverse of a matrix. You can cross verify with this answer, and you must have got the same answer. That is the inverse of a matrix M1. So okay with it. So both the answers are correct, and you also got the same answer. So we'll go ahead and we'll see the next question. Determinant of a matrix M1. So here, determinant of a matrix M1 is 0.999. If we round it up, we get 1. Then next question number 4 was to find out trace of a matrix. Okay. So how we define trace of a matrix is total the sum of diagonal elements. So we can calculate 2 plus 2, 4 plus 1, 5 plus 2, 7. Yes, this is the correct answer. That trace of a matrix is 7. After that, we have rank of a matrix. So all the four rows or four columns were independent of each other. And means the rank of a matrix is 4. So I hope it is clear to you all now, and all the matrix operations which we have studied today. There is transpose, inverse, determinant, trace, rank, and you can successfully apply it on a given matrix, and you can even cross verify whether the answer is correct or not. So is there any doubt on this today's topics? You can write it in the chat window. We'll take the questions if you have any doubt on today's topic. Okay, there is one question asked by Rahim. He says that why there is a decimal after each number in the inverse. Actually, according to the definition of an inverse, what he said is inverse is, okay, so we have defined what is the definition of inverse. Inverse is equals to what? 1 divided by determinant of matrix. Okay. This is 1 divided by determinant of matrix multiplied by what? Adjoint of matrix. This is the definition. And according to this definition, what happens is, this is the operation 1 divided by, which converts every number to be multiplied by the floating point. Okay. So remember, whenever there is a division operation involved, you will always have the result as a floating point number by default. If you want integer, then explicitly you have to convert this floating point number into an integer by using a type conversion operation. Okay. Otherwise, whenever in a mathematical operation you try to perform a mathematical operation which involves division, then in that case the result will always be a floating point. Okay. And in case of an inverse, the output will always contain a decimal. Okay. If the values are displayed, if the values are like, say it is 2.00000, then the value may not be displayed. If the value is 2.1234 something, okay, value may be displayed. Okay. And hence the point will always be there to indicate that by default data type of this inverse of a matrix is floating. Okay. So this dots after each number represent that this inverse what we have calculated by default is of data type float, right? And when you explicitly convert it into the integer, then you will have this 4 numbers. There is a question from Ashish. Are you asking this question on the same matrix M1? Okay, then M1 says determinant inverse will not exist now. Why inverse does not exist now? We have this matrix and we have a determinant is equal to 0.99999. It has a value now. When you round it up, okay, I told you when you apply round up operation on this, it will have a value 1. Okay, if you round up this 0.99999, you have a value 1. If this determinant will have been, listen, if determinant will have been a value that is 0.123, that is less than 0.5, then in that case, the inverse will not have been existed. Okay. So here determinant is 0.999 and hence 1 upon 1 or 1 upon 999 is not equal to infinity, and yes, inverse will always exist in this particular case, right? So I hope now all the topics from this lectures is being clear to all students and there is no doubt further. So I'll have one homework for you. You can try this and you can calculate all these operations so that the function calling and use of particular function, the application of each of these functions will be very clear to you all. Okay. So here it is a question. All of you note down the matrix. So I'll say this is matrix M1 with 5 columns and 5 rows, right? So we have increased the size of a matrix with 5 rows and 5 columns, and the question will remain same from today's class. That is, you have to calculate the transpose, inverse, determinant, base, and rank of this matrix. Okay. Note down the question, and then we'll stop.